Let's look at acid catalyzed opening of an epoxide, similar to the reaction I've shown here where we mix an epoxide with an acid and a nucleophile. And whenever we add an acid to an organic compound, we should always think that one of the first things, if not the first thing that's going to happen, is that the acid is going to find electrons to interact with. And the H+ finds those electrons on the lone pairs of this oxygen. So the lone pair of electrons on that oxygen react with that H+, giving us our protonated epoxide. Now we can look at a three-dimensional model of what that protonated epoxide will look like, and I've drawn that over here. And what you'll notice is I've color-coded my groups to make it easier to keep track of things. So my methyls are green, my ethyl is blue, and so on. And this is our simple model of that protonated epoxide where the oxygen has picked up a hydrogen. It now has a positive charge. Well, this simple model is actually not the best model because that oxygen is going to pull on the electrons in these other bonds because it's a very electronegative atom. It doesn't usually bear a positive charge, so it's going to pull electrons away from the carbons that it's interacting with. And what we need to decide is which of these two carbons it's going to pull more electrons away from. And what you'll notice is that this carbon has one other substituent on it, a methyl group, whereas this carbon has two other substituents on it. The more substituted carbon is going to be able to better stabilize a positive charge. So the electrons in this bond are going to be pulled towards the oxygen more, and more positive charge will build up on this carbon. In our three-dimensional model, that's this carbon right here, and we can look at that in this model right here. This is a more accurate representation of the molecule, the protonated epoxide. This is actually what I get when I minimize the previous model using a molecular modeling program. You can see that this bond is stretching. The epoxide oxygen carbon bonds are no longer symmetric, and we're pulling electrons away from this carbon right here. And that carbon is going to have more positive charge on it. What happens next is that our nucleophile will come in and react with one of these two carbons. And when we think about which carbon that this nucleophile will react with in the case of the protonated epoxide, it's the opposite of the case that we saw in nucleophilic opening of an epoxide in the absence of an acid. In that case, it goes to the less sterically crowded carbon. In this case, it goes to the more substituted carbon because there's more positive charge building up on that carbon. So the nucleophile attacks here, and these electrons go to the oxygen. We can look at those arrows in our three-dimensional model. So this is our nucleophile. This is the carbon with more charge on it. You can see the nucleophile comes in from one side, and the epoxide leaves or opens up from the other side. If we look at the product that we get, what we see is the nucleophile is pointing in one direction from the bottom as I've drawn it here, and the new OH that forms is pointing up in the opposite direction. We can also look at that in our three-dimensional model. As this nucleophile starts to react with this carbon and starts to form a bond here, this bond starts to break. As that happens, this ethyl group starts to move up, this methyl group starts to move up, and these move down until we get something sort of like this. And you can see that just as we saw on the other diagram, the nucleophile is pointed in one direction and the new formed alcohol is pointed in the opposite direction.